Okay, hello everyone to our last but not least talk in track number 2. So with me today is a good friend, Fabio Tiriticco, and I already said your last name is too long. Get a last name with 2 letters. You know, it's just easier, much easier.
I know, I'm sorry about that.
Yeah, it's fine. It's fine. So Fabio and I actually know each other from, I don't know which one exactly, but from
Yeah, a
one of
very
the
long time.
million community
What was it?
events. Software Circus, probably one of the meetups.
Yeah, can't recall, but you were a panelist at one of my meetups as well. So we go
Yeah,
way back.
yeah, we go way like 6 months or something. No, it's been longer than that. But yeah, so Fabio is here with us today to tell us about deep learning, which I'm very excited about. So I don't know what exactly you're going to be speaking about, but it's you titled it Planespotting. Can
Yes,
you tell us a little bit about that?
yes. So my talk really is an introduction to deep learning with a very specific case of, well, spotting planes. So actually, a word of caution, this is really meant for beginners. So if you already know everything about deep learning and AI, this is probably not a good talk for you.
Sounds good. I'm still going to watch it. Cool. So if you're ready, Fabio,
I
then
am.
yeah, take it away.
I'll maybe just remove my patch because it's making me dizzy and I want to pass out during the presentation. Oh, much better. All right. Well, so welcome everybody to my talk, and thanks to the organizers for having me, um, and thanks for all the work that they put into this. I'm really grateful for being here. Very quickly, who I am. I'm obviously a pirate, even though I got both eyes still. I work as a software engineer in Amsterdam, where I'm also a community manager. I run the Reactive Amsterdam meetup, where I probably met Lian a while ago. And I'm also one of the organizers of the Kubernetes Community Days Amsterdam, which this year we had to unfortunately postpone and in fact finally canceled due to the pandemic. But yeah, so that's me more or less. And the planes idea, where does this idea come from? I want to share a little bit of backstory with you. So this is a map from Google Maps, is a section of the surroundings of the Amsterdam airport, Schiphol. Now, what you can see is that lane, this lane that I highlighted now is the first lane that was built, is the original airport area. Now, when traffic grew and it expanded, they decided to build another airstrip, and that's the one that you're seeing highlighted now. But as you can see, in the meantime, there was already a highway there in between called A4. So the solution to make these two airstrips communicate efficiently that they found was build a bridge that goes right over the highway and the road. So the end result, which was the view from my office where I worked about a year ago, is this. From my office, I could see this bridge where these immense planes, they just stroll peacefully on, and they are like meters just above these little cars and humans that pass under the bridge. So I don't know, I was just so super excited by this view, by this sight every time from the window. And at the same time, you never know when these planes are passing by, right? Because they pass every now and then, but they don't tell you when they're about to pass. So here's my idea. I'm gonna put a Raspberry Pi next to the window that takes pictures of that bridge. And then I want to train a neural network that is able to tell me whether there's a plane on the bridge or not. And when there is, I am going to tweet it. So this is the idea in a nutshell. That was for me to combine this excitement for these planes, but also learn about AI. So here we start our adventure. This was the setup of my Raspberry Pi. You can see there's a plane on the bridge now. And this Raspberry Pi would take a picture every so often, say every minute or so. And as you can see on the right, you have a plane on the bridge and the picture on top, and no plane on the picture at the bottom. And so I want to train a network that simply tells me, all right, now there's a plane, now there's no plane. To go ahead, we need to understand a little bit, what do we mean by deep learning? What is it? So deep learning is a subset of machine learning, which itself is a subset of artificial intelligence. And deep learning is also a synonymous for neural networks. So, where you have all these neurons connected to each other, we'll get there later. And so when we look at machine learning and deep learning, basically the idea in short is to extract patterns from reality, so data coming from the real world, and find patterns and be able to understand what these patterns mean, and be able to make sensible predictions, or acknowledge something, find link between things in general. And well, if we specify that, the two common uses for machine learning or deep learning are basically two. One of them is regression. And regression basically answers the question, how much? So in the graph below, you can see we can establish a relationship between the inputs on the x-axis and the outputs on the y-axis. This could be, let's say, I don't know, the median house price given its square meters, or in general, just a function that maps one input or more to one output. And then the other use case is classification, which answered the question, what kind? And this image, you maybe seen it already. It's the famous experiment to try and train a deep learning network to distinguish Chihuahua dogs from blueberry muffins. And I mean, myself, I have trouble. I'm not sure sometimes whether it is a raspberry muffin or a Chihuahua. So to train a network that does this requires a lot of effort. But yes, so we have these two cases, regression and classification. And our case, going back to the plane, it's a classic classification use case where we have two classes, two possible outcomes, which is there is a plane or there is no plane. Now, how are we going to build from scratch our deep learning network? Now, for me, the first revelation about deep learning networks was that this kind of AI is still at a stage of kind of trial and error. So there is no way to deterministically build a neural network that will for sure work fine with your use case, the plane in this example. We only know really that for some problems, certain deep learning architectures work better than others. And there's many different architectures, and each one of them, as I said, they match some specific use cases. At least this is what we have found with our experience. There's unsupervised pre-trained networks, convolutional neural networks, recurrent neural networks, and many more. And in this talk, we're going to focus on convolutional neural networks that are the standard de facto state of the art for image recognition. They are one of the reasons why AI in the past few years saw this explosion of cases and applications. So for instance, if you think about just about anything, think about a Tesla, or like in general, a self-driving car. It's probably full of convolutional neural networks that are in charge of seeing the street signs, the horizontal street signs, but also the vertical street signs, and so forth. So our goal for this talk is to build from scratch a convolutional neural network. Now, before we get there, we just need a little introduction to the basics of neural networks. And as you can imagine, the very, very basic unity is the artificial neuron, so called because it resembles the biological neurons that we and all animals have in our brains. So what is this neuron actually? Well, in fact, it's not that complicated per se. Basically, an artificial neuron is a mathematical function called transfer function that receives a set of weight inputs. So in this screen is W1, W2, applies this transfer function to these inputs, and the result of the transfer function, which confusingly enough is called net input, but it's kind of the outcome in that sense. Anyway, the result of this function gets put through another function called activation function. This activation function has basically the role of deciding whether to let the information contained in the net input pass through, to propagate this information. So typically, a neuron can have either 0 as an output or the result of the transfer function. That's more or less it. And so after all, it's just a mathematical function. Of course, we're not going to see in detail what that function is, but it really is just a function. So you might be wondering, all right, well, this neuron doesn't seem all that powerful. What's the big fuss about? Well, the thing is, these neurons get immensely powerful when you combine lots of them. So this is a typical example of so-called multi-layer neural network. Why multi-layer? Because if we try and read this network from left to right, you see we have on the left some input values that can be anything. And then there's one input layer, which is usually a number of neuron, an amount of neurons that corresponds to the inputs that we have. And these neurons of the input layer will typically just propagate the information through to the first hidden layer. Now, the first hidden layer is made of the neurons that have these transfer functions. It can decide whether to propagate the information to the second hidden layer. And then finally, we can have more hidden layers than two. And then finally, there will be one output layer, which is basically whose task is to collapse all the information coming from the last hidden layer, in this case, hidden layer 2, take this information, collapse it, and output some values, which will be the outcome of this prediction, let's say. So as you can see, when the hidden layers are more than 2, and when each hidden layer has many more, hundreds or thousands of neurons, this becomes really, really powerful. Well, in practice, let's look at an example. Let's say on the left, our input values will be A, B, C. Then our input layer will just propagate this information fully to the first hidden layer. And then maybe for this input on the hidden layer, first one, only some neurons will propagate information to the hidden layer too. And then at the end of this, the same happens for the second hidden layer, and the output layer, well, our output values will be 2 and 5. If we, on the left, change our input to T, P, and G, well, the input layer will just propagate it through, but maybe the hidden layers will behave entirely different, generating output values that are now 7 and 1, let's say. So one of the reasons, actually, you see now why these types of networks only exploded recently is because only recently we got to have the computational power necessary to train networks like this with thousands and thousands of neurons where all these combinations are practically infinite. Now, I know we are still a bit vague, but now let's get a little bit more specific with this idea in mind into the convolutional neural networks, the ones about the image. So what is their power? What makes them special? Well, look carefully. How about this next slide? I am sure that as soon as you have seen the image on the right, your brain immediately knew which one was the rabbit and which one was the cat. But if you were to try and reconstruct the process that happened into your brain, it would be quite difficult. And most of it all, how would you teach it to a computer? Your brain must have gone through steps like, okay, those are two animals. They both have white and black fur. They both have two ears. They both have two eyes. Both have 4 legs. Both have 1 tail. But there are differences. So maybe the rabbit ears are a little longer, and the cat has the eyes in the middle, where the rabbit has his eyes on the side, and things like that. And maybe the cat's tail is a little longer. So you must have gone through all of this and finally decide that which one was the cat and which one was the rabbit. But if you were to break this down, I tell you, it would be very, very difficult. Well, the power of convolutional neural network is that when they're trained with enough images, and by enough images, I mean a lot of images, thousands and thousands, they are able to automatically extract features, understand what makes a rabbit, and combine all these features. So if we go a little deeper on this rabbit idea, let's say you have all these images that contain a rabbit. Our convolutional network will basically apply filters to these images during the training phase with thousands of images. Our network will apply filters that will scan the image. So imagine that the grid that you see on the bottom left image is, that grid is at the pixel level. And this network will be able to apply some filters that somehow scan this image and understand what is the rabbitness of rabbits, what makes them unique. It would be, I just want you to focus on this for a moment. It would be so hard to teach algorithmically a computer to see a rabbit. And this is where the power of convolutional neural networks come from. Now, a typical convolutional neural network architecture with reference to the multi-layer architectures that we've seen earlier looks sort of like this. The inputs, our image comes in from the left. We will have an input layer that will propagate the information, and then a convolutional layer, which is the layer that scans the image with these filters that we have just mentioned. And then there's going to be a subsampling layer immediately after that. The subsampling layer basically just sort of reduces the bandwidth of the information coming from the first convolutional layer. Then after the first two, there's going to be another convolutional layer and another subsampling layer. They do exactly the same work. They scan the image and then they shrink this information. In our cases, the subsampling layer just have the information into. And then finally, we'll have one dense layer of 500 fully connected neurons. And those neurons will eventually collapse their information into the output layer, which will tell us, in our case, whether there is a plane or not. So once we have identified the architecture that we want to use based on the use case that we want to solve, then all we have to do, and by the way, it's a lot of work, is to grab training images. So in my case, I took, with my Raspberry Pi, lots and lots and lots of images of planes and classified them one by one, telling here there's a plane, here there's no plane. And once you have these training images, well, in fact, also what I did is I cropped them around the area that I wanted to work on, which is the bridge where the planes are on, and to reduce computational power necessary. I also reduced the resolution, scaled it down. And then once you have this data set, what you want to do before giving it to to use it to train your neural network is to split this data set in two. So 80% of your images will be used to train the network, and the remaining 20% will be used to test your network. So you want to see how your network behaves with images that it has not previously seen. Now, so far, so good. How are we going to implement this in code from scratch? I used a library called Deep Learning for J. There is really no reason why you use this compared to other libraries, namely TensorFlow is a very famous one. I tried TensorFlow, but I didn't really like their APIs very much. Deep Learning for J is made expressly for the JVM. And so for me, I'm a JVM guy, and I really felt at home with it. So I went with this. But of course, there's many alternatives. And so I've chosen my library. How are we going to do about that? First, we need to tell our network a few informations. So the input height and the input width, that's the size of my image. these numbers are, by the way, completely arbitrary. They could be anything else. I don't know why I chose this one. They look so weird, in fact, but maybe there was a reason back then, but they could be anything. Depth, in this case, 3, is the number of input channels. So each pixel will have 3 values, R, G, and B, so 3 color values. And this will be our depth. And more settings, like the number of possible outcomes. In our case, is 2 classes, either plain or no plain. And then we are going to finally build our network. This is the image we have just seen before, and we're going to build it layer by layer. Now, the code that you're going to see is in Scala, but it really looks like Java, really. So you should have no problem following it. There's only one caveat. What you're seeing here in these few next steps is pseudocode. So if you just take the code on the slides and try to compile it, it won't work. But the full code is available. I have a GitHub repo. We'll share the URL later, so you can look at it and try and run it, try to tweak it, and experiment with it. So here we go. We start with creating a classic Java builder, a neural net configuration builder, and then we want to add our first layer, the input layer. Oh no, we add directly the first convolutional layer. A couple of things here. When you see new convolutional layer.builder 5 and 5, what are those 2 5? Well, remember that earlier I said that our image applies filter, our network applies filters to our image to detect the unique features of, in that case, it was a rabbit. In our case, it will be a plane. So 5 and 5, that's basically the size of the filter. So 5 pixel by 5 pixel. The image will be scanned with this 5 by 5 pixel area. We set up the stride. Stride is actually how fast this image moves. So we're going to move 1 pixel by 1 pixel. And this is our first layer. Then next we add the subsampling layer, which is going to basically, you see all those 2, is going to just half down the information coming from the previous layer. And then we add another convolutional layer, another blue layer there in the middle, just the same as the first one, with a subsampling layer just after that, which also will have the bandwidth again. And then finally, our dense layer, 500 fully connected neurons. And after them, the output layer, which will output our num classes. That's basically 2. And this is how, oh, and then finally, yes, we set some more information, like the input height of the width and the width of the image and the depth that we set before. And this is it. So now on the left, you see maybe it's a bit small, but that's the full convolutional neural network that we have built. The next thing that we want to do is train it and see how it behaves. So training is basically a combination of 3 elements. There is a configuration that we're passing to our trainer, which tells us basically how long the training should go on for. When you train a neural network, what you do is basically the network tries to tune its neurons and its inputs and the inputs of each neurons basically forever, and it keeps trying to improve. So in this case, we're going to tell him, say, after 10 minutes of training, you're going to stop. We're going to pass to the trainer the model, so the CNN model that we just built, and we pass them all the images, all the files, and we'll get the best model. So originally I had planned a live demo with the Raspberry Pi, but due to these conditions, here's a screenshot for you of a typical training run. Now, if you read it from the top, you see completed training epoch 0, and then a certain score, and then epoch 1, and another score. So an epoch basically is an iteration, is a full training through all the images that we have given the network. And then each iteration will produce different values on those inputs of the neurons. And so each iteration will have a different score. What this trainer does is it takes a score, and the best score is kept through the training. So at the end, if you see at the bottom, it says that it hit the end of the training because it was training for, in this case, 6 minutes. And so we choose the best result, the best configuration that we achieved so far, which in my case, in this screenshot, is the epoch number 5, I believe, yes, with 0.96. You might be wondering, what does the score mean? It's basically, in this case, you can choose, but it means accuracy. So how good it was between discriminating plane or no plane on the test images. You remember the 20% that you didn't use for training. Well, so I created a neural network. We trained it with those images. What are the results? Well, the results is, in fact, I was able to sort of successfully detect planes on the bridge. And there is this account on Twitter called Planes on Bridge that I created. And every hour, it was posting a picture of a plane. I tweeted about 1,100 tweets, and there's 11 followers. So maybe not the most popular Twitter account ever. Mostly my friends, family, and a couple of fake accounts. You're welcome to give a look. I don't tweet anymore because I don't work in that office anymore. But the results were sort of okay. And one last thing that I want to touch on is, how do we evaluate the performances of my neural network? Well, if you look at one prediction done by this network, say you give it an image, and then the network tells what it thinks that there is in the image. Well, the outcome of the network can be classified to 4 different results. It could be a true positive in the top left quadrant. The true positive is when there was actually a plane and the model correctly saw it. But just below that, it could be a false positive, which means the network thinks that there is a plane, but there isn't any. The result might be a false negative in the top right quadrant. So there was a plane, but the model didn't see it. Or finally, just at the bottom right, it could be a true negative, where there was no plane, and correctly the model didn't see one. Now, another huge work that you have to do with deep learning networks is see what their outcomes are, what the network thinks, and compare it with reality. And that's not a huge work. You need to see the images and the outcome that they give about it, and then classify it. And so I've done that too. And there's a few key measurements that you can do on your network. We're going to look at 2 of them in this graph. One of them is the precision, which is basically the amount of true positive divided by the sum of true positive and false positive, which basically tells us how well the model avoids false positives. And then the other measure is the recall, which is how well the model avoids false negatives. In my case of this network, you can see the blue line is the precision, and it's pretty high. Often it's 1. So that means that in that day, it detected on that day, when the model sees that it was a plane, there was always a plane, 100% right. And then some days, it's not so high. We'll see on the next slide why. But the red line, the recall, which means how well the model avoids false negatives, it's very variable and it's not very high. So that means that my model missed quite a few planes. There were planes, but the model didn't see them. And so when does it go wrong? Why is that? Well, being in the Netherlands, it's mostly the weather, unsurprisingly. Weather conditions can change dramatically the perception of my network. So for instance, you see a very foggy day on the top left image, and the top right image, it's raining. So there's drops on the window, and the image is very confused, which confuses the network a lot. In the top, sorry, in the bottom left image, actually, it's a very sunny day, but the sun is just in front, like directly shooting into the camera. So the contrast is really high and everything's black. Actually, if you squint your eyes, there is a plane there in the bottom left image. There is a plane, but it's very difficult for the network to see it with this color that are all sort of flattened. And then also, finally, if you look at the bottom right image, it's easy for us. Of course, there's a plane on the bridge, but it's only the part of a plane. So the network has, it's a lot more difficult for a network to see that there's a plane where maybe you see only a bit of it. You see only the tail or only the front. It's partially hidden. And if you look at this, it really should make you realize how powerful our brains are. It's so hard for a neural network to understand that there's a plane when the head is missing. But for us, we have no doubt about it. And well, there's another thing that I want to touch here, why the network goes wrong sometimes. And it's the AI bias. I was based in Schiphol in Amsterdam, the Netherlands, and the national airline is KLM, and its planes are blue. And so that means that there's a lot of blue planes around Schiphol, a lot more blue planes than planes of other colors. And now this might remind you of some tragic cases from, the earliest experiments from maybe 10 years ago from Google or Microsoft, where networks would produce racist sort of results and discriminating results. Well, even with a funny, playful project like mine, I was able to touch AI bias. When there's a blue plane on the bridge, my network is like, oh yeah, sure there's a plane, totally, I see it. But then when there's a white plane or a yellow plane from DHL or whatever, the network has a lot more troubles. And this is because the training set is heavily skewed towards blue planes, just because that's what I saw the most. And so, yes, this issue of AI bias is really, really important. Create a a properly balanced training set for AI training is extremely difficult. It shouldn't be left to chance. It's very difficult. I don't have the solution, but I hope that we as humanity, we move some steps towards a way to reduce AI bias. Well, that was it for my introduction. What are the next steps for you? If you find all this inspiring, I would say find a fun use case and a data set. That is the URL where I posted the code that used for my project. And also the training set of my planes is there. Learn more about deep learning and convolutional neural network. And then I would suggest think about a use case in a domain that you know well. So maybe it's a domain that you work on, or it's a domain that you love. Maybe you love, I don't know, flowers. My girlfriend loves plants in general, so that could be a great domain. And then experiment with it. Think about a use case. References, for me, that book, Deep Learning, A Practitioner's Approach from O'Reilly, it's not very new. It's from 2017, but the foundations are very solid and they haven't changed. So I would really recommend it. And below you have link to the network, the library, Deep Learning for J that I mentioned. And again, that's my GitHub URL. And so thanks. This was my talk, and I hope I inspired you to look a little deeper into artificial intelligence and deep learning.
Thanks, Fabio. That was great. I really loved it. There's one question that I can see. It's by Sriram, if I'm pronouncing your name correctly. and he asked, how often do you sample images in a day?
Right. So thanks for this question. I started with sampling one image a minute, but the bottleneck was myself, because at the end of the day, I would have really hundreds and hundreds of images to label. So I scaled it down, and I think after a while, it was maybe one every half an hour or so. I ran this for a few months. At the end of the day, at the end of my project, I had a training set of about 16,000 images, all painfully classified and labeled one by one, looking at them. Here there's a plane, here there's no plane. And that was it. So 16,000 is probably starts to be enough to train a neural network correctly. But if you look at the, the proper sort of professional training set, we're talking about from 50, 60,000 images up.
Wow. Okay. Thanks for that. Free Rum. Hopefully this time I got your name right. So I think we are a little bit over time. So I think there's no time for more questions. Over on track 1, as far as I know, Ian Coldwater is getting ready for their talk. So thank you so much, Fabio, for joining us today.
Thanks for having me.
Of course. Thank you all. This is my last engagement as well. Thank God. I can't wait for my glass of wine. Yeah, I was also super... Thanks. Super happy to be part of this. Really had a great time, and hope that you enjoy the rest of the conference. And hopefully we'll see each other very soon in some real life situation. That would be nice. I miss hugging people.
Yeah, me too, so much.
Okay. So, okay, signing off here, and see you soon.
Bye.
Bye.